the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. And in this video, we're going to talk about, at a pre-calculus level, a composition of functions, specifically the domain of compositions of functions. This should be a review, so most of this material you have seen before, but I'm going to treat it as though you're about to enter calculus so that you can see the level at which you need to be by the time you get to calculus. The level you need to be at is what I should have said. So I'm going to read a few things here. As opposed to arithmetic combinations of functions, and this is something that I already talked about with my students in my class. So at this point, you should already have a strong familiarity with the arithmetic of functions, adding functions, subtracting them, multiplying them, dividing them, and looking at the domain of those. Finding the domain of a composition of functions involves careful consideration and a little bit more critical thinking. Consider the composite function f of g of x. If we follow the order of operations, which is critical to our success in mathematics, then our initial consideration is the domain of g of x. Well, actually, technically, I suppose the initial consideration is x, but really you kind of step outside of those internal parentheses to the next set, and you look at that domain right there. And usually that's pretty simple. But then you have to consider the more complex question of what's the domain of f of g of x. And this involves looking at the output of g of x and asking yourself, are the outputs of g of x going to cause issues for f? So there are fancy ways of saying this. The theorem that you see below is a fancy way of really considering the domain of a composite function. The domain of a composite function f of g of x is a set of those inputs x in the domain of g for which g of x is in the domain of f. In kind of layman's terms, basically means look at the domain of g and restrict your domain to that, and then furthermore look at the outputs of g and see if those have problems when you plug them into f. That's really what that means. So let's go ahead and jump into kind of a big example here. And this might require extra paper, but for now, we'll just take a look at this. So we have f of x, g of x, and h of x that have been handed to us. And we want to find the compositions f of g, g of f, f of h, and h of h, and in each case we want to state the domains of those functions. Then in the end we're going to go ahead and choose one of them just for giggles and graph that in Desmos. So in this first case we're going to look at f composed with g. Now I have to admit I really hate this notation. I find it's much easier if you work with f of g of x. Just a lot cleaner. So let's see. F itself is the natural logarithm. And then what we're plugging into that is the function g. Now, to be honest with you, there's actually a better way of writing this, believe it or not. You could, so this requires a little bit of your prerequisite knowledge with logarithms. You should know from your prerequisite material, if you're in a pre-calculus course, your Algebra 1 course, or sorry, your Algebra 2 course should have taught you the following. The natural log of a over b is equal to the natural log of a minus the natural log of b. The property of logarithms there, or some people call it a law of logarithms. So you could technically take that logarithm right there and break it into the difference of two logarithms. It'd be the natural log of the numerator minus the natural log of the denominator. So I'll go ahead and write all that out. You should also know, again, from your Algebra 2 course, so as people move forward, I really do try to hold to your prerequisites. You should know the natural log of 1, or even the logarithm base a or base b of 1 is 0. So that natural logarithm of 1 just turns into the number 0. So this turns into a negative natural log of 3x squared plus 17x plus 10. Now, this is a very interesting problem. I like this problem a lot because we might be able to actually factor, again with prerequisite material, we might be able to factor 3x squared plus 17x plus 10. Let's just try it, right? So factor, I write all my prereq information off to the right hand side. We have 3x squared, plus 17x plus 10. And so I think this should probably factor, well, I don't know if it factors honestly, but if it did, it would be either a 5 and a 2 or a 2 and a 5. That's those products of those numbers become 10. And if you look at the multiplications, 15x and 2x, yeah, definitely you can combine those to become a 17x. So therefore, we know that this will be a positive 5 there and a positive 2 there. And so we even have that this natural logarithm, the argument of it, factors further into 3x plus 2 in quantities times x plus 5. All right, so that even can be simplified further. So notice that it's not as simple as just saying, oh, I'm going to plug G into F and I'm done. Those days are gone. As you move towards calculus, you have more and more complex computations involved in what you do, and you have to use all of your prerequisite material to kind of simplify these statements. So I'm going to go ahead and remind you of one final, actually really it's not the final, but one semi-final property. The log of a times b is the log of a plus the log of b. So if you take a look at this, it's actually a negative log. So it's not going to be log of a plus log of b because we're going to multiply both component pieces by a negative. It'll be a negative log of 3x plus 2 minus a log of x plus 5. That is a very simplified version of f composed with g. If you take a look at actually the two versions of this, the first version being the natural log of just 1 over this 3x squared plus 17x plus 10, that is actually a very simple statement. However, to compute with that can be a bit of a mess. Versus our final statement, there's a lot of power to compute with this. However, there are some issues. So let's talk about the domain of f composed with g of x. We'll start with, so now I'm focusing, I'll use blue, no, I already used blue, didn't I? I'll use green ink to talk about the domain. So let's start with the innermost function. And the innermost function is this 1 over polynomial. Now, luckily, we already know how that factors, that denominator factors. So we require that that denominator not be 0. Or in other words, we want to find out when that denominator is 0 and throw that out so that we don't have that within our domain. So we require that 3x plus 2 not equal 0. I'm just going to say equals 0 for right now because we'll solve that and then throw that outside of our domain. And then also x plus 5 cannot be 0. But again, I'll set it equal to 0 and then just make the statements here that x, we have a problem when x equals a negative 2/3, and we also have a problem when x equals a negative 5. So that's with that yellow highlighted function. That's the domain of g. And in fact, it might be nice to write that up above g here. So the domain of g is all x not equal to negative 2/3 or negative 5. By the way, if you were to write that on a number line, you would find out that your domain is all real numbers up to -5, not including it. Then from -5 to -2/3, and then finally -2/3 to infinity. So that's what I'm going to write down for my domain here. Is all real numbers up to -5. Skip over -5 and continue on until you get to -2/3. Skip over -2/3 and continue on until you get to infinity. That would be the domain of G. I'll say D sub G. That's the domain of G. All right, so we found that domain. We got to throw two x values out of our possible domain here. But then you realize I've only worked on the interior of that. Now I have to worry about the exterior of that, the logarithm itself. You have to ask yourself, where is the logarithm undefined? Or better yet, where is the logarithm defined? What is the requirements that you would have to plug into the logarithm? So what are the restrictions for the argument of the logarithm? And we happen to know that, I'll write it this way, but the natural log of happy face, I'll just say it that way, requires happy face to be greater than 0, strictly greater than 0. So again, this adds into this already complex looking problem another step, that we require not only that our fraction here not be divided by 0, but it has to be actually positive. So let's go ahead and do that. Sorry for the grainy screen. I'm actually projecting this onto a different monitor and then capturing that. It's a bit of a mess, but whatever. All right, so this implies we require 1 over 3x squared plus 17x, what was the last piece? Plus 10? Plus 10, we require that to be positive. Another way you could kind of talk about this is that since the numerator is already positive, you're requiring the denominator to also be positive. That should make sense to you, that positive over positive is positive. So this would imply that we require 3x squared plus 17x plus 10 to be, oops, not greater than 10, but positive. There we go. Easy fix. Just get rid of the 1. So we require that to be positive. Luckily, we have some work done here. Now, if you're not a student of mine, you probably don't know how I teach this, or if you have not been a student of mine very long, you probably don't know the tricks that I use to this. But this right here, if you were to graph that, that is a parabola. I don't think anybody would argue with that. And we're asking, when is that parabola above 0? Above x-axis. So when is parabola above the x-axis? That's really what that mathematical inequality is asking or stating. It wants to know, when is that parabola above the x-axis? And we're lucky enough that we already factored that parabola and found out that it became 0 at -5 and -2/3. We already found that out. But in addition to finding that out, we happen to know that because it's a positive 3, this parabola opens up. There's supposed to be a plural on that. It opens upward. So without even really doing a precise sketch, at least I get a rough sketch that the parabola looks something like this. It's an upward opening parabola. It has x-intercepts at -5 and -2/3. And I am just asking the question, when is this parabola above the x-axis? And you can see it right there. There's not a lot of work to this problem once you know how to do this. It is above the x-axis for x equals -infinity all the way up to -5. And from -2/3 to positive infinity, we need it to be strictly above the x-axis, because if it's not, it will be at the x-axis and the denominator here will be 0. So we require that we're strictly above the x-axis. So we're discluding or not including these 2 points. And now you actually have the set of x values that you would plug into the argument here so that their outputs are still positive, so you can take the natural log of them. And that will give you the domain of that composition. So the true domain of f of g of x is negative infinity, that highlighted region right here, all the way up to -5, not including -5, gluing onto that via union, -2/3, all the way to positive infinity. The idea of finding finding domains of compositions is pretty much running that way throughout all of mathematics. You look at your functions you're using to compose, you look at their domains. For example, the domain of f here is everything from 0 to infinity, all x values from 0 to infinity. You look at those domains and you start kind of building them out. Notice the domain of g included everything except for -5 and -2/3, but because of the restriction that it was being plugged into a logarithm, we needed the regions where that domain was going to cause g to be positive. And that was -infinity to -5 and -2/3 to infinity. That middle region is where that parabola is negative, and that won't work out for us. A lot to digest there, but kind of important topic. So let's go the other way around. Let's look at g composed with f. Now that is not going to be a fun problem, but let's go ahead and try it out. I'll need a new sheet of paper for this. And as I mentioned before, I really detest this notation, so I will trade it out. It's just g of f of x. And I don't hold it against your professor if they love that notation. It's just something that doesn't work for me. And we will go ahead and take g, which is 1 over 3 times something squared plus 17 times something plus 10. And for those somethings, I will plug in f. Just natural log of x there and a natural log of x there. Now this sort of can be simplified because if you think about it, this is still factorable. It is still like 1 over 3u squared plus 17u plus 10, where I performed the u substitution, u is equal to the natural log of x. And then we know that can be factored. So I will go ahead and write this as 1 over 3u plus, I forget, I think it was, this one was the 2, u plus 5, yeah, I think that's right. And then in the end, just remember, if you do this style of simplification where you take a pattern and you call it u, you have to resubstitute in the end to kind of get back to your original form. So this will be 1 over the quantity 3 natural log of x plus 2 times the quantity natural log of x plus 5. Now that is the composition. And now we're super interested in just finding the domain of this composition. And again, start with the innermost parenthesis, f of x. F of x was the natural log. And so we already know one domain restriction. I'll write it off to the right-hand side here. We know that x must be positive. That's because the domain of the natural log is everything from 0 to infinity. It's all positive real numbers. Now, we take a look at the next step, and the next step just requires, when we look at the outer function, g here, g is that rational function here, and when we plug the natural log into it, we have already simplified down to this business right here. Once we get here, we still have to say x must be positive, but there might be other restrictions. And the other restrictions here are that you can't have division by 0. That's really the only other restriction. So 3 times the natural log of x plus 2, well, that cannot be 0. Or you could say it equals 0 and solve. It doesn't really matter to me. It does, because if you set it equal to 0 and solve, then you're basically saying I'm finding out what x values cannot be in my domain. So if you prefer that, I will do that. I think most of American students do that. So I'll subtract 2 and divide by 3. And I should say this implies, and I'm subtracting by 2 and dividing by 3. So when you get to there, you find out the natural log of x cannot be a negative 2/3. Now, again, you should, from your prerequisite information, know that natural logs can take on, as far as their outputs, any real number. So it is okay that the natural log becomes a negative 2/3. There is a solution here. You should also know from your prerequisite material that the log base b of x equaling some output is true if and only if, that was a terrible bijection symbol there, sorry about that, let me do that again. If and only if, and I call this the circular argument, b raised to the y power is equal to x. So if and only if b to the y is equal to x. That's actually how logarithms were developed back in your Algebra 2 course several semesters ago. So when you come back over here, you know the base of the natural logarithm is e. So this will imply via that circular argument that e raised to the negative 2/3 is equal to x. Or in other words, we will restrict our domain so that e to the negative 2/3 is not included. We'll do the same thing for that natural log of x plus 5. We know that that cannot be 0. So you could either say it cannot be 0, or you could just set it equal to 0 and solve. I'm not going to write the subtraction there because you guys can see it. And again, circular argument, e to the negative 5th must equal to x. So these are our 2 additional domain restrictions. So right now, with this problem, we actually have 3 kind of critical domain restrictions. We have x must be positive. It cannot be actually a negative e to the negative 5th, and it cannot be e to the negative 2/3. Combining those, do not leave it like this because this is ambiguous how I've written it. You want to actually state the domain. So here I go. The domain of, what do we, G composed with f is, well, you know that it has to start at 0 because it, again, this top restriction, we're required that x be positive. So, okay, great. And it'll climb all the way up until you get to the next, I should say, domain restriction, which is e to the negative 2/3. That occurs before, oh wait, hold on, no it doesn't. E to the negative 5th actually happens before e to the negative 2/3. And that is because e to the negative 5th is 1 over e to the 5th, and e to the negative 2/3 is 1 over e to the 2/3. Between those two denominators, this one is larger, so that's a smaller number. So our domain will go from 0 to e to the negative 5th, and then we're going to skip over that and then continue on the other side of it until we get to e to the negative 2/3. We'll skip that and continue on the other side of it until we go off to infinity. Notice I have restricted my domain, so it's not including e to the negative 5th, it's not including e to the negative 2/3, and it only contains positive numbers otherwise. That is the true domain of that composition. Now, I think that some students, especially in my class right now, because we haven't reviewed logarithms, might say, oh, am I supposed to remember that? Yes, you are. You've had now 2 courses prior to this with logarithms, so you've had plenty of experience with them, so you should be able to do this. So yeah, that can be expected of you. Now the next one, we've already done f composed with g, I'll cross that out, and g composed with f. The next one is a kind of a doozy. It's f composed with h, f being the natural log, h being the sine. So let's go ahead and open up a new sheet of paper for that. F being the natural log and h being the sine. So I'll write that here. F of x is the natural log of x, and h of x is the sine of x. Well, that was supposed to be an equal sign, but didn't quite make it to that. So now we are going to compose f with h, so that's f of h, which again is like the outer functions and the natural log, and the interior function is the sine of x. And that's actually pretty much as good as you can get with that. You can't simplify that any further. Yay, that's done. But now you have to start talking about domains. And we already know that the domain, I'll actually just do it as d sub h. The domain of the function h is equal to all real numbers. You can plug anything you want into the sine function. We know that from our trig, so we're okay there. Then we step outside of that sine function and now look at the logarithm and ask ourselves, what is our restriction for the logarithm? In other words, what can we plug in as an argument to the logarithm and what can we not? Well, we happen to, again, we've written it already, but the domain of f is all positive real numbers. And that's a problem because the sine, which is what we're plugging into it, bounces between -1, which that is not a -1, and 1. And so we're going to have to restrict our domain for sine so that it can only return positive values. And to do this, it's going to require graphing the sine and taking a look at patterns. Remember, we want, I'll even write that down, we want, or we need actually, a sine of x to be positive. So let's graph the sine of x. This is very similar to earlier when I graphed that parabola. I said I need that parabola to be above the x-axis. So we need sine of x. We need sine of x to be above the x-axis. This kind of logic you need to build before you step into calculus. You have to be able to do some very complex problems that involve quite a bit of critical thinking. So going ahead and graphing the sine curve, I'm not going to do like an excellent graph. I will just do a graph. And I'll oscillate this guy right here. And I didn't want to do that, but I'll do this. Just prepping for something here that I know is going to happen. Now, you do know that the period of the sine curve naturally is 2 pi. So, and you also know, whoops, that where it starts, I'm going to start it actually back here. It starts at 0, 0, and then it climbs and then falls and oscillates from there. So this value right here is pi, here's 2 pi, here's 3 pi, back here is negative pi and negative 2 pi, so on and so forth down the line. And we want to restrict the x values so that our sine curve is strictly above the x-axis. Let me just go a little bit further here just because I want to. This will be 4 pi right there. So if I erase everywhere where it's below the x-axis, you get that weird restriction. You see all those values, like those, that's where the function's above the x-axis. And by the way, it goes forever, so those are not the only values. But to be strictly above, I'm putting open circles at these points. And I didn't say what that was, but nobody cares. So we have to find a pattern so that we can state what the domain of our composition is. Our domain requires that the sign be positive. Well, it seems to be positive from 0 to pi. I'm going to write that down below. It's positive from 0 to pi, and from 2 pi to 3 pi, and from 4 pi to 5 pi. I hope you can see a pattern from negative 2 pi to negative pi. If you can't see it, take a look at the coefficients of pi in the first coordinate. The coefficient here is even, 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 even. So every interval where the sign is positive starts with an even coefficient on pi and ends with an odd coefficient on pi. -1, 1, 3, and 5, and you can guarantee it's going to be, next one will be 6 to 7, and so on and so forth. So, the domain of our composition, we're going to build it in steps here. Domain, whoops, that's domon, so let's actually change that. Domain of, I forget the function names, f of h is, well, the set of all ordered pairs, I'll just say A to B, such that A is even pi and B is odd pi. If you haven't seen this notation, it's called set builder notation. You actually do not have to use it here. I'm just showcasing a different kind of notation. But you can actually kind of clean that up by remembering something about even numbers. An even number is just twice an integer. And an odd number is just twice an integer plus 1. And again, that's where k is an element of the set of integers. So, a better way to write this is to say, well, you know, the domain of our composition is the set of all intervals where the intervals are 2k pi all the way up to, whoops, that was supposed to be a pi, all the way up to the next odd number, 2k plus 1 pi. Now, if k were 0, I should also mention where k is an element of the integers. Now, if you take a look at this, name any integer you want, -10, for example. Well, that means we have an interval that goes from -20 pi to -20 plus 1, or -19 pi. -20 to -19 pi, and that is going to be where the sign is actually positive. So this interval, with its notation that k is an integer, is actually descriptive of all the intervals where the sign is positive. So there you go. That's a nice problem to do. Very complex, but still I think it's the right level for a pre-calculus class. Now going back here, we can see now we're done with all that. We just have one last one. Hcomposed with h. This is actually sort of the easiest of the group, honestly, and I'm going to do it on this page. Hcomposed with h is sine composed with sine. Hcomposed with h is just sine composed with sine. It's almost too silly to do. You know that the domain of sine, what you're going to plug in here, is all real numbers. And then the outputs for the sine, whoops, that's not what I want to do. The outputs for the sine function just vary from -1 to 1, which are fine to plug into a sine function. So again, I can plug any real number into this innermost parenthesis because the sign can take on any real number. So now imagine that this turns into any real number, or sorry, this turns into some number, let's call it n, where n is between -1 and 1. Is there a problem with that n being plugged into sine? Not at all, because again, sine can take any number as its input or as its argument. So, there are no domain restrictions on this composition. So, this is the true domain of Hcomposed with h. So it's not that every composition leads to a restriction, just some. Now, I did say go ahead and choose one of the compositions and graph it. Now, this is totally your choice. You can go to Desmos and graph whichever one you want. I kind of am curious to see the natural log of the sine of x, because that just seems like a fun problem. Before I do it, I just want to mention that if you're in a calculus course of mine, I might just ask you to graph this by hand. I don't know why. It's kind of a jerky move. I totally get it. But there's something about this that can be done sort of easily. For example, we're about to plug in x values that go from 0 to pi, let's just pretend, into, remember our function is, where is it? The natural log of sine of x. So if we're going to graph the natural log of sine of x, let's just start by thinking about what it looks like from 0 to pi. Well, let's take the middle part at pi over 2. If I were to plug x equals pi over 2 into the sine of pi over 2 is 1. The natural log of 1 is 0. Now I'm going to plug in a value that's really close to 0, but not exactly 0. And the way I'm going to note this is using this notation. In fact, let me actually clean that up a little bit, because that's a little messy. So let me clean that up. I'm going to maybe write it down below. The natural log of the sine of something near to 0, but still above 0. So that's like the sine of, let's say, 0.01 or something like that. Well, we know as values get close to 0, you can see it here, as values get close to 0 for the sine itself gets close to 0. So this little picture right here is getting really close to 0. You should know from your algebra that the natural log, as its arguments get close to 0, drops down to negative infinity. So, as this argument gets really close to 0, this natural log is going to drop down to negative infinity. The same thing is going to happen. I know that students are looking at this going, oh my gosh, am I supposed to totally understand this? No, I'm trying to open the door to calculus right now so that your brain can handle calculus. So you have to be at this level by the time you get to calculus. This is like day 2 in my calculus class. So here, let's look at the natural log of the sine as x gets really close to pi. It's not sine of pi though, it's getting really close to pi, but from the left-hand side of pi. So pi minus a little bit. So instead of 3.14 blah, 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 it might just be 3.1. Well, you could see just via the graph of the sine, as x values are getting close to pi, the y values are getting close to 0. So as x values here are getting close to pi, the sine, the y values, are getting really, really close to 0. But still on the positive side of 0. And again, looking at the natural log graph over to the right, as our arguments, our inputs, get really close to 0, the y values for the natural log drop down to negative infinity. So this will approach negative infinity. Now, I don't expect you to graph this by hand. The problem stated, use Desmos, but I want to showcase that using a little bit of logic can have you do a graph of this by hand. Here's my number line. I will just mark the y-axis right here. This is x equals 0. I'm also going to mark the x equals pi right here. And what we said was, at pi over 2, halfway between, the sine of pi over 2 is 1, natural log of 1 is 0. So it should look something like this at pi over 2. But then we said as the x values are approaching pi, the y values drop down to negative infinity, and the same thing over here. And by the way, there should be an open region in that pattern will repeat from 2 pi to 3 pi, because the pattern repeats for the sign on that. So it should look like this. So I'm looking for my Desmos graph to look something like that. Now, do I expect you, or do I expect my students to be able to do that by hand? In calculus, yes. Today, no. But we'll go ahead and graph it out. I'll just type it as f of x. You could actually, I think the graphs were that f was natural log. So let me do that. F of x was the natural log. You could totally do it like this if you wanted to. And I think that it was h of x was the sign. Is that what it was? I think that's right. And now what I'm going to do, you can see both the functions right there. I don't want them. What I want is f of h of x. And I'll turn off the other two. And look what I have. And if I were to draw vertical asymptotes at x equals pi, and x equals 2 pi, and x equals 3 pi, and I like to kind of really color my asymptotes red, so I'm going to go ahead and do that. And I also like to make them dash dotted. Dash. Dash. And I like this function to be black. And I really, really dislike having the grid on there. You now see that we have the actual graph that I just did. This is where you want to notice it's missing the graph between this is x equals pi and x equals 2 pi, because again, that's where the sign goes negative and you can't plug that into the natural logarithm. This level of graphing is where you need to be at once you get to calculus. You need to be able to think critically and graph like this with compositions. It's not that you're always going to do that, but it's an exercise in mental agility. So I would really appreciate it if all of my students could start kind of building stuff like this. It's actually pretty neat to see that you could do it. Just try it out. See if you could do it. Anyhow, that's enough for this lecture. And we'll continue on with another lecture a little bit later. All right.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.